So it's very difficult to conclude such a session after all these fantastic presentations, but I will try to make a very short presentation on my vision of the future of this personalized digital patient. We've seen a lot of its facets this morning and this afternoon. And I will try to make a prediction. So, of course, for predictions, you have to be very cautious, especially when they are recorded. And prediction is always difficult, especially when addressing the future, as a few people already mentioned. So my first prediction will be an easy one. It will be the fact that there will be more and more images and signals for this digital patient in the future, and that will have more and more evidence-based medicine, as was mentioned by Doreen before. Medicine based on measurements, objective and quantitative observations. It will create an even larger overflow of information, and so there will be even more need for computer-assisted extraction of the information which is clinically useful. And we've seen in the presentations already how difficult sometimes it is to extract this clinically useful information. There will be new modalities still to be invented to cover all scales, from the molecular scales to the cellular scale, to the organ scale and the whole body scale. Who could have thought only 10 years ago, for instance, that we would be able today to visualize the living cells? And for instance, if you look at the middle video here, that we would see in a benign cyst on the pancreas, the circulation of the red blood cells in the capillaries in real time. And that we would be able today to measure the progression of cancer, for instance, in vivo and in situ. So beyond this type of confocal endomicroscopic images, there will be more use of images like optical coherence tomography, more use of elastography also to get the biomechanical properties of tissues, a still further exploitation of MRI with higher fields, spectroscopy, thermometry, diffusion, perfusion, and so on. There will be a larger exploitation of the magnetic and electrical field produced by our brain, by our heart, with a special equipment that can be worn all the time, for instance, and sending signals to your smartphone connected to the hospital. There will be the development also of what is called theranostic imaging, combination of diagnosis imaging and therapy imaging, like, for instance, the use of highly focused ultrasounds that can be guided by diagnosis ultrasound, or the development of nanovectors that encapsulate contrast agents so they can be traced, and also encapsulate a drug that can be delivered on demand with the use, for instance, of focused ultrasound. Progress will also be driven by technology advances and technology leaps. We have to think of the power of computers, for instance. During the past decades, they have followed the Moore's law, which means that every year and a half, the performance have been doubled. It means 3 orders of magnitude in 15 years and 6 orders of magnitudes not in 1 million years, in 30 years. And this year, for instance, the most powerful computer is able to perform 35 millions of billions of operations per second. It's 3 million times faster than Deep Blue, who already beat the champion, the world chess champion in 1997. And it's predicted that in 5 years there will be exaflops, 1 billion of billions of operations per second, and probably in 34 the zetaflop 1,000 times more. Visualization is making a lot of progress. We've seen many examples. It's already possible in the OR to manipulate the virtual patient directly in front of the patient. It's even possible to manipulate without any contact using, for instance, the TheraPixel technology, similar to the Kinect technology that we've seen before. It's even possible to immerse the Jedi into in front of the virtual personalized heart, for instance. And robots also will play a more and more important role, not only to interact with the patient, but also, and for which we've seen the importance of augmented reality to help guiding, for instance, the insertion of the arms, but also to help the manipulation of the instruments themselves. But also robots, as Nasir presented, will play a very important role in the imaging itself. For the so-called intraoperative images. Also a very nice combination here of the use of robotized fibroscope and advanced mosaicing techniques to create a larger field of view by just placing the probe, the robotized probe, directly in contact here with the liver of an animal. And finally, this very nice project led by Sébastien Ourselin at UCL on robotized fetal surgery, guided by endoscopic imaging. Again, a very nice collaboration between robotized flexible endoscopy and endoscopic imaging to do very delicate surgery on the fetus. So there will be also, and that's a third prediction, more and more biophysical modeling at all scales of anatomy and physiology. And we've had this very nice presentation by Peter Hunter this morning, the presentation also by Olivier Faugeras, the presentation by Mike Brady. And so there is now this VPH Institute in Europe trying to promote these research efforts. There will be more and more personalization of these biophysical models, developing new data assimilation methods to customize the large number of parameters of these models. We see examples here in computational oncology, in computational neurology, computational cardiology, in digestive surgery, and interventional radiology. There will be also more biophysical simulation, which really appears more and more as a new pillar for research. To better understand the disease, to better predict the evolution, to better plan and optimize the therapy. And the more realistic the models, the more useful will be these simulations. And we've seen, Doreen has shown how this type of model can help predict the benefit, for instance, of resynchronization, providing in advance, in fact, the expected benefit for the patient, and try to know if there is any hope that the implantation of biventricular resynchronization therapy will be useful or not, and also if there is some optimization in the placement of the therapy. There will be also, we're talking about big data, but there will be even bigger data with very large databases of images available on the web with attached expertise. I have listed already a number of databases that are made available to the scientific community. And these databases will be generalized in the future, and they will be even augmented by data simulated with biophysical models. And here I just show an example, for instance, of a real MR sequence of the heart with no model, which is transformed into a simulated MRI where there is now the exact motion prescribed by a biophysical model, and this type of data can be generalized. There will be more machine learning. We've seen a lot of it, for instance, the presentation by Antonio this morning. And for instance, this is really the basis of the success of the Kinect, the training on very large real and synthetic images, more than 1 million of images. And there are already results on, for instance, the simulation, the training, and the prediction of tumoral cell density from simulated MR images of tumors, or here the simulation of, the prediction of depolarization time from observed motion in real and simulated cardiac images. I believe there will be also more and more so-called smart atlases, that is very large databases of images with the expertise attached, and content-based image retrieval algorithms that are able to retrieve in the database images with a similar appearance, and to help, in fact, guiding the diagnosis, like opening a book atlas directly at the right page. And here it's an example in 2D. We've seen examples in the talk of Daniel with 3D images of the brain. And it will be generalized, for instance, to 4D cardiac images, taking into account not only the appearance, but the shape, the motion, the evolution from time series of images. There will be also probably closer links between scientific communities, not only between informatics, computational sciences, and other sciences like mathematics, physics, chemistry, with biology, with medicine, but also within informatics, probably with a community of database, security, certification of software. It's interesting to look at the links between computer vision, for instance, and the MICAI community, MICAI for medical image computing and computer-assisted intervention. Here is the distribution of the keywords of the accepted paper at a recent MICAI conference, and the distribution of keywords for a computer vision conference. And the distribution is not the same, but we retrieve, for instance, segmentation, registration, learning, detection, tracking, shape, sparsity. But despite all these correspondences, which make, in fact, very fruitful the collaboration between the two communities, the community of medical image computing and computational medicine remains very unique thanks to this magic or golden triangle, where we have this academic pluridisciplinary research on one vertex, the necessary collaboration with clinical partners to really define useful problems and validate them, and also, very important, the collaboration with industrial partners, especially in this field, where not only the industrial partners can help making a research prototype into a real product, but also they contribute to the definition of the fundamental problems, and by creating new technology, new imaging technology, for instance, they really drive a number of research problems. So I will conclude with this slide on the city of Nice, where MICAI was organized in 2012. It was organized in Japan last year. It's going to be in Boston next September, and in Germany in 2015. And this is really the community of this new research field, which is supported by a young research community. For instance, about 40% of the participants to this conference are PhD students or very young doctors, and I think it's a sign of the vitality of this research domain. So I want to thank all the speakers of the symposium today, who've really presented outstanding research and have made outstanding presentations. There is an illustration by Kajal here on the slide. And I also want to thank a number of people. I want to thank all the members of the Asclepios research team who have helped me prepare all the courses I presented here. I want to thank Gérard Berry for all his very precious advices and the fact that he attended almost all the lectures with a lot of enthusiasm. I want to thank all the services of the Collège de France who have been absolutely fantastic. I want to thank Marie Chéron, who is responsible for the chair, for all the facilities, all the help she provided. Julie Béret, that all the speakers know here, who's been extremely helpful. Cécile Barnier, Mr. Debon, and the whole service here, and of course also all the persons who did the translation of the presentation. So thank you for your participation and for your attention.